So, coming to the home stretch here. So, let's see. We will have one makeup lecture, unfortunately. Weather got the way. But we will have a makeup lecture next week on Monday at the usual time. And I haven't gotten confirmation on the room, but I will discuss that, trying to get the scheduling fixed, and I'll email you if something has changed, okay? Everyone's paper's due, so I'm sure you're putting on the final touches now. And we'll look forward to seeing that on Monday. All right? All right. So, last time we were talking about the discovery that in laser cooling, when one gets to these low temperatures associated with polarization gradient cooling and the subdoppler mechanisms, that in fact the temperatures are so cold that the atoms become trapped in the optical potentials associated with the standing waves that are created in what was called optical molasses. And one of the experiments that demonstrated that was looking at the spectrum of the light that was scattered in the process of laser cooling itself. And what we discussed last time was that if I looked at that scattered light and thought about it in terms of atoms absorbing a laser photon at some frequency and then emitting some scattered photon at some frequency, that there are processes that are associated with the atom absorbing and coming back to the same vibrational level, in which case those are called elastically scattered photons. And then there are processes that have to do with going up or down the ladder of vibrational states. And what was observed in those experiments was that almost all of the light was elastically scattered. And there was some small amount of light that was scattered at frequencies that were one oscillation frequency above or below, where the oscillation frequency associated with the motion of the atom oscillating in the trap. And we discussed that from a kind of classical picture, thinking about the atom as a kind of antenna that is moving. And so there is a phase modulation, and that phase modulation then gives what are called side bands on top of the main oscillation. And the fact that the vast majority of the light was scattered into the elastic peak is associated with the fact that the motion is very small compared to the wavelength. So they're trapped near the bottom as well, because remember that the scale of this is the optical wavelength. Moreover, what we see is that the width of these peaks is fairly narrow. That is to say, these sidebands are well resolved, and that what we discussed that as what is known as lambdic narrowing, which is to say that if we thought about the lifetime broadening that we've discussed, kind of the time energy uncertainty perspective on the line width, we might expect this line width to be on the order of the scattering rate, because that's the rate at which these transitions are made. But in fact, they are much narrower than that. They are down by a factor which is known as the Lamb-Dickey parameter squared. And that Lamb-Dickey parameter is associated with the localization of the wave packet relative to the optical wavelength. And you remember what we discussed, thinking about that from just thinking about quantum mechanical perspective, the transition rate between some vibrational state to some other vibrational state was related to something having to do, was proportional to the overall scattering rate, which is what you would say if you were not bound. But in addition, there is a factor associated with the recoil. So if the recoil is all in the z direction, then there is a factor having to do with the absorption of a photon giving a translation in momentum of h bar k. So the overall transition rate depends not only on the scattering rate, but whether or not you can go from some initial state having to do with the motion of the atom, absorb that recoil, and go to the final state. If you're in free space, there's no problem. You go from one momentum state to another. But if you're bound, well, then there's some gap here, okay? And moreover, we can think about that in momentum space, and thinking about if we looked at, say, the transition, for example, from the ground state to the first excited state, it doesn't matter, all of these have the same basic principle, then the initial wave function is some Gaussian in momentum space, which has a width that's on the order of h bar times whatever the width of the wave packet is. In this case, the ground state wave packet, right? When we absorb a recoil of momentum, what we do is we shift this wave packet by some amount. That amount being h bar k. But if h bar k is much, much smaller than this initial width, well then basically I haven't done anything to the wave packet. So if I then try to say, what is the overlap between this dotted curve and the first excited state, which is, looks like the Hermite-Gaussian, the overlap between this dotted wave packet and this antisymmetric one, or in fact any of the others, because they're all orthogonal, right? All of the Hermite-Gaussians are orthogonal to the ground state. There's no way I can go there. And so there is a reduction having to do with this Lamb-Dickey parameter, which is given by the width of the wave packet in units of the optical wavelength in units of 2 pi. Okay? Right. So, all right. So this, these experiments, this was in the early 90s, led to, well, before I do that, I should say we should get a little bit more of a sense of the parameters, just to get a feeling of things, about the numbers, because that'll give us some indication about some other direction we might head. So before we get into the next subject, let's just get a little feeling for the numbers. How big is the oscillation frequency of the atoms inside these potential wells, inside these standing waves? So what we have here, let's just think about this. Suppose we have a simple standing wave. with some amplitude. So let me define that the optical potential, say along the z direction, has some peak-to-peak depth sine squared kc. Okay, so this potential is a standing wave, has some peak-to-peak height, and this is my standing wave. Okay? So, first question, how much is the oscillation frequency under the harmonic approximation? So if we can approximate this as a harmonic oscillator. So we want to expand this around the origin. And set that equal to the potential associated with the harmonic oscillator, where n is the mass of the total mass of the atom. So if we solve this, what we see is that h bar omega oscillation is equal to twice h bar squared k squared over 2m times the peak depth. That's h bar omega squared. So the oscillation frequency in energy units is twice the square root of the peak-to-peak depth times the recoil energy. Okay? So for example, if my peak-to-peak depth was 100 recoils,
the 2 should be, the root should be over the 2 too.
did I get this right? Hold on a second. No, this should be 4. Because I get this right, because I multiplied by 2, and then I have over 2 again. So x. I do remember that 2's out front, so that is correct. Weird things happen. Anyway, all right. So if I had a 100 recoil deep lattice, then my h bar omega is 20 recoils. How big is the recoil energy? Well, it depends on the atom, right? Because it depends on the mass of the atom. I know what it is for cesium, because that's the atom I've always worked with, and that's 2 kilohertz. So this is about 20 kilohertz. That's an acoustic frequency, or maybe a radio frequency, for a 100 recoil lattice. Of course, it doesn't go up very fast, right? It goes up like the square root. So if I had 1,000 recoil deep lattice, then this would be, I don't know, what is it, 65 or something like that kilohertz. So that's the scale of oscillation. That's a lot less than, say, in an ion trap, where you have much, much tighter binding because you're trapping not a neutral particle but a charged particle. There you have megahertz types oscillation frequencies. How localized is the ground state, say, of such a, if I were thinking about this like a harmonic oscillator, approximating this as a harmonic oscillator? What is the width of the ground state? So you remember from basic quantum mechanics that the ground state has a wave packet width related to the mass and the oscillation frequency, right? Everyone remembers that one? I can re-express this in terms of the Lambdicki parameter associated with the ground state. And that is equal to h bar squared k squared over 2m divided by h bar omega oscillation. So the Lambdicki parameter associated with a particle trapped in a harmonic oscillator has a very simple form. The form is, it's the square root of the recoil energy divided by h bar omega oscillation. So that's another interpretation of Lamb-Dickey effect, is that when the recoil energy is small compared to the gap, then I can't make that transition because I can't absorb that recoil because there's an energy gap. In free space, I can do so, but if I'm trapped, then I cannot. So notice, of course, here, this also means that the localization of the atom wave packet is a very slow function of the depth. If you want to compress this wave packet, well, you're going to need a lot of optical power because of the scaling here. If I look at this, the oscillation frequency goes like the square root, so the Lamb-Dickey parameter goes like 1/4 power. So if you really, it's very hard to get very, very tight localization unless you're pretty close to resonance. But then if you're pretty close to resonance, well, certainly not going to be able to do suboptical cooling. And so we have some feeling now about the fact that we can get these atoms cold and trapped near the bottom of these lattices, near the bottom of these wells, and that led to the idea that, hey, look, what I have here is something analogous to a crystal. I have a periodic potential which can trap a particle, like thinking about electron transport in a crystal. And that led to denote this configuration as what's now called an optical lattice. So, optical lattices. Well, as I said, they were born out of thinking about subdoppler laser cooling and the observation of localization in the optical lattices. However, these days, and soon after their development, what was considered was, let's separate the cooling process from the trapping process. Instead of thinking about this as what happens in the context of laser cooling, let's just try to manipulate the atoms moving in space through a conservative potential, which means we're going to have our cold atoms somehow coming out of optical molasses, subdoppler optical molasses, and actually these days, and we'll talk about this on Monday, coming out of a Bose-Einstein condensate. And then wrap those atoms in a far off resonance optical potential that creates an optical lattice. So let's define an optical lattice. So what we mean by an optical lattice is a periodic light shift potential for cold atoms created by a set of interfering laser beams. So the simplest example of an optical lattice is drawn right there. the simplest example is a 1D standing wave. Now, the picture that I just drew up here doesn't really tell the whole story. What I thought about is, well, each of these are a bunch of sort of local harmonic oscillators. And there's some oscillation frequency, there's some localization of the wave packet. But we know that, in fact, in principle, we can get tunneling. In fact, the energy level structure associated with the atoms in this optical lattice is not what's drawn here, but in fact involves energy bands. So let's try to get a feeling for what's going on here. Remember, if you remember from your basic quantum mechanics that if I have a periodic potential, then there are bands of energy separated by energy gaps. How big are those? Well, we can get to a few simple estimates here. Suppose I just think about this from the point of view of just thinking about two wells with some depth of some barrier between them. Okay. In our case, this is a standing wave, so let's call this the peak-peak height that we were just discussing. So how might you estimate this tunneling rate? Want to have an idea about that?
The overlap of the Gaussians.
It's certainly going to depend on that, indeed. I mean, one way we could do it, which it's similar to the kind of analysis that we studied a little bit earlier when we're looking at, for example, we were looking at diatomic molecules in some of the homework problems, right? And when we were looking at something like neutral hydrogen, and we wanted to calculate what the energy spectrum was that. And we had two localized electrons around two localized nuclei, and then we wanted to calculate that spectrum. We could use a variational calculation where we minimize the energy associated with two localized particles and diagonalize that like we did in homework. And when you do that, what you find under this variational calculation, this is related to that. This is what you get. Now, this is in fact, as we wrote over there somewhere, the relationship between the oscillation frequency and the peak-to-peak depth in the context that we think about this as a standing wave. We see that this factor here is just related to the Landicki parameter, right? Because the oscillation frequency is related to the peak-to-peak height. So this factor here is e to the minus 2 over the Landicki parameter squared. So that means that this e over e, the delta e over e recoil scales is something like 2, this over e recoil. It's 1 over the Landicki parameter squared. It's another square root to square root of 2 over lambda parameter cubed. So as Jean was saying, this in fact is related to thinking about the overlap of the wave functions comes in through the this is correct. Yeah. The overlap of the wave functions, the overlap of these Gaussian wave functions sets the rate of tunneling. So if I have a deep enough lattice, well then I will suppress the tunneling. But certainly as I get up into the higher energy bands, tunneling becomes much faster and the bands become much wider. In fact, we can solve the band structure for this problem quite easily. Let me just remind you of a few things about periodic potentials and band structure. So recall Bloch's theorem. So what we're looking at here is the problem of we're solving for the energy levels. We have a Hamiltonian, which involves the kinetic energy of the atoms and the periodic potential. In this case, the periodic potential is a very simple potential. But in general, it's periodic with some period L. In this case, L is half of the optical wavelength. Right? And so we want to solve, in this problem, we're looking for the solutions. Well, let me not put an index on here. Let me just say, we're looking for the energy eigenvectors, right? So recall Bloch's theorem says that if I have a periodic potential, then the eigenstates must respect that symmetry because the momentum operator is translationally invariant, which means that if I translate by one period, the wave function, the eigenstates of the system, can only change by an overall phase. That's Bloch's theorem. So, from Bloch's theorem, well, that tells us that I can write an ansatz for the wave function, now thought of in position space, having factor out a part that gives a constant, a phase for a translation and a periodic function. So my function u here is periodic. And what modulates it is a plane wave with what is known as a quasi-momentum. So this function satisfies the criterion that the wave function can only change by a phase under translation. Because if I translate this function by one period, this stays the same, but this shifts by a phase. So as you recall, in a periodic lattice, the particles look kind of like plane waves, but modulated by periodic functions. And these are known as the Bloch functions. And that gives rise to the band structure associated with the energy levels inside this periodic potential. So if I were to sketch that, well, those energy bands are a function of the band index n and the quasi-momentum. Now the energy eigenvalues are thus functions of those two indices, where Q is a continuous variable. The n's are discrete variables. And the periodicity of the lattice leads to the fact that the energy eigenvalues are periodic in Q with a period dependent on what's known as the reciprocal lattice, which is 2 pi over L, L being the period of the lattice. In our case, L is lambda over 2, so this equals twice the Laser wave number in the particular case that we're looking at the moment. So if I were to sketch what the energy eigenvalues are as a function of Q for different values of n, they have the following form. Since they're periodic, we only need to look at it within one period of the reciprocal lattice. And that's typically done between minus k over 2 and k over 2. It's periodic with period k. If I had just harmonic oscillators, well, I have some energy levels, but that's not what we see. What we see, in fact, is continuum of levels. Which look like that, with a band gap, but which is a little bit shallower. At the Brillouin zone edge, remember, this is known as the first Brillouin zone. I don't used to know that. I used to know French. So, what we have are very thin bands having to do with the fact that tunneling is small near the bottom, and then the bands get broader as I get higher in energy. Of course, this picture depends to some degree on how deep is the potential relative to the 0-point energy. I might have only one band in the whole potential. It depends how deep the potential is. Okay, so the point here, what really started to excite people was that we now have an analogy between cold atom motion in optical fields and the motion of electrons in crystals. And one can think about simulating or studying the effects that are traditionally considered in the context of condensed matter physics, now in the context of cold atom physics. And that's really been one of the, a real hot area of research in the last 2 decades. So let's talk about this a little bit more generally. So we have, by general optical lattice, we want to think about this now in terms of we want to think about this in terms of higher dimensions, not just 1D. But there's another important aspect of this, which is the dependence on atomic spin. Why? Well, how would we write down a general optical potential? Well, the optical potential, the light shift potential, as a function of position, we've studied. It's the potential associated with the induced dipole moment when I'm inside an optical field. So we have -1/2 the induced dipole moment, it's a function of time, dotted into the electric field at the position of the atom. And then we time average. That's the light shift potential that we've discussed. In fact, this light shift is a light shift operator, generally, because the dipole depends on the internal state of the atom. Okay, so let's suppose that we have a monochromatic field. This is my laser field. It has a single frequency to start. My induced dipole moment is also depends on the local field and the polarizability, which in general is a tensor. And when we plug these two things in together, what we found was this is equal to -1/4 E star alpha dot E. Right? So, we have the general form of the optical potential depending on an arbitrary configuration of this field, at least for the case of a monochromatic, but it also depends on the polarizability of the atom, which depends upon the internal state as well. The polarizability, we found, depends on the dipole matrix elements and the detuning. In fact, if I have a general optical lattice, I need to think about the fact that there might be multiple excited states that I am detuned from. For example, there can be hyperfine structure in the excited state, and I'm detuned at some level between each of these excited states. It could be a different detuning. So I have to sum over all the possible excited states. Here, these dipole operators, as we studied in homework, are related to the dipole operator projected between some potential manifold of ground state levels and excited state levels. So I might have different magnetic sublevels in the ground state and different magnetic sublevels in the excited state, and I have to think about the projection between all of them. Let's take a look at this in some simpler case. So let's consider the case of, suppose we look at an atom which has a ground state angular momentum 1/2, and an excited state angular momentum 3/2, the kind that we were looking at in the context of Sisyphus cooling. Okay? So we have these kind we've studied before, where we have a sort of nuclear spinless model of the D2 line of an alkali. We have the spin up and spin down potential associated with the ground state, and then undetuned somewhere. All right, so what can we say about this? Well, as we studied in homework, it is potentially useful, you get used to it a little bit, to think about this effect in terms of the different irreducible components of the polarizability tensor. So recall the irreducible representation. We can decompose our light shift potential into components having to do with the irreducible tensor components of the polarizability. We have a part that is a number, which I'll call alpha 0, a part that is an antisymmetric tensor. Before I do that, let me perhaps write this out in a slightly different way. The components of the tensor were a number times the identity matrix, an antisymmetric matrix, which can be written as such, and then a term that was symmetric and traceless, which is the irreducible rank 2 component. Right? So we studied that earlier. So if I plug this in to that expression, I get that my light shift potential is a term that's a scalar term. It's a number. It's independent of the internal state of the atom. That comes from plugging this in here. Then I have this term, which looks like, if I write out all the indices, it has the following form. It's a vector I'll call alpha 1 dotted into E star cross E. And then a term that is the irreducible rank 2 component. All right, let's take a look at this. Firstly, what we see, if, depending on the strengths of these different components, determines something about the nature of this optical potential. Firstly, we see that there's a term here that depends only on the intensity. It has nothing to do with the polarization. Okay? So regardless of the polarization of the light, I have this term, assuming alpha 0 is not 0. This term, what happens if I have a linearly polarized field that's everywhere linear? Well then, E the electric field is a linear polarization. That's a real vector. And the vector crossed into itself is 0. So if I have linear polarization, in fact, I could, if I rewrite this as the amplitude times the polarization, then this term over here is the square of the amplitude E star cross E. Right? So if the polarization is linear, this term is 0. If it's circular, it's not 0. So this has something to do with the elasticity of the light. And this, well, who the hell knows what that is? Come back and we're going to ignore that because this thing, we're going to look at this in the context of spin 1/2. For the spin 1/2, what we said was that we studied this in homework. It was everyone's favorite problem. And we found the following things. What can I say? Oh, yeah. So the scalar part, which is, you know, it depends, it's the identity operator, times some number, which is 2/3 alpha naught. Where alpha naught is the reduced dipole matrix element associated with the polarizability, and this 2/3 comes from the Clebsch-Gordon coefficients. Alpha 1 was equal to, well, notice firstly, you can take a look at this and you see alpha is a Hermitian operator. Therefore, when I take its transpose, I have to get the star, right? Since this is anisymmetric under I goes to J, this has to go to minus itself when I star it, which means that it has to be proportional to the imaginary I. So it's I, and it comes out to be minus I 1/3 times the sigma matrices. With an alpha naught on top. All right, so, and alpha 2 is 0. Because this is spin 1/2, it can only have a scalar and a vector. It can't support anything more. Okay, putting that together, let's take a look at this expression. So this becomes equal to all right, something I'll call V naught times no, there's 2/3 here. And the 1/3 V naught. Sigma dotted into so what did I do? What I did is I just plugged in this expression for the amplitude. I have a term here, the scalar term, and I have a term here that's the vector term. So what can we learn from this expression? Well, what we see here is that there is a term here that is independent of the spin of the atom, and there is a term here that depends on the spin of the atom. whether the atom is spin up or spin down. In fact, this optical potential here has the form of a constant term plus a term that looks like a fictitious magnetic field. What do I mean by that? Well, if you think about a spin 1/2 particle and you think about its interaction with a magnetic field, how would you write that down? A magnetic interaction is minus mu dot b, right? And the mu of a spin 1/2 particle is proportional to its spin. It's proportional to the sigma matrix, right? So this would be equal to, twice the g factor, mu b, the spin. And the spin is the sigma matrix over 2. So, what we learn here is that the optical potential has an effect associated with circular polarization that acts like a fictitious magnetic field that interacts with the atom. This means that the optical lattices are fairly rich structures that depend not only on the external motion of the atom, but also its internal state. So let's look at this for some specific case. Let's suppose I have a 1D optical lattice. And that optical lattice now is going to be created not by a simple standing wave, but by standing wave with a polarization gradient in it. So here's my counterpropagating laser beams, which create an optical potential as a standing wave. However, I'm going to say that one of these polarizations is in the plane, and one of these polarizations is out of the plane of the board by some angle theta. Okay, so it's supposed to be out of the plane, rotated. If it was 90 degrees, it would be limb perpendicular. If it was 0 degrees, it's limb parallel lit. So, you get my picture? What is the optical potential associated with this for this atom? Assuming red detuning. Well, one way to do it is to do it the way we did limb per limb. We can decompose this into sigma plus and sigma minus, right? And then we could say, well, there's a potential associated with sigma plus on this spin, and there's a sigma minus on that spin. But with the tensor decomposition, we have it straight away. What is my laser field? Let's look at it in this form. So my laser field here is equal to E0 e to the ikz times vector E1 plus E0 e to the minus ikz E2. Right? Those are the two counterpropagating fields with two polarizations. We can plug this in, get the intensity, and take the cross product to see the fictitious magnetic field. Here's the answer. here's the answer. Let's understand what it means physically. We have two terms here. The scalar term and the term that came from the vector line shift. The vector line shift here depended on the cross product here. The cross product between the two vectors goes like the sine of the angle. The dot product between the two vectors goes like the cosine of the angle. The cross product here, the direction of the cross product is the direction of propagation, the z direction. So the direction of the fictitious magnetic field is along the propagation direction. It's along the z-axis, because that's the cross product direction of E1 across E2. So sigma dotted into that gives me a sigma z. So let's look at this in a few different cases. When theta equals 0, then we have a pure standing wave, right? We have linear polarization everywhere when theta is 0. So theta is 0, the sine is 0, I get V is minus 2/3 V naught, V naught being a positive number times 1 plus cos 2kz, or minus 4/3 V naught cos squared kz. Okay. What happens when theta is pi over 2? Well, when theta is pi over 2, that's ln perp ln. In ln perp ln, well, there's no modulation of the scalar part because the intensity is everywhere constant. What varies in space is the fictitious magnetic field. So in that case, what I have is my potential is minus 2/3 V naught times the identity operator minus 1/3 sine of 90 degrees is 1, V naught sine 2kz sigma z. So I have now a light shift operator, which is spin dependent. Depending upon the atom, whether it's spin up or spin down, it sees a different optical potential. That's what we studied already in the context of Sisyphus cooling. This is a formal description of that, which gives us a kind of deeper picture of what's going on in terms of this vector part of the polarizability. So this is equal to, if I put in the identity operator, is spin up plus spin down projectors, and sigma z is spin up minus spin down projectors, then my optical potential has the form minus 2/3 V naught minus 1/3 V naught sine 2kz spin up plus minus 2/3 plus 1/3 V naught sine 2kz spin down. So, what do we see? I'm going to make you a little plot here which shows the optical potential for different values of the angle between these two polarizations. When the angle is 0, what we have is something that's better chalk. Let's hope this. Actually, do we have two colors around? Yeah, sort of. Try. So the two potentials in this case are right on top of one another. These are supposed to be. So this is spin up, and this is spin down. All right? Here's the origin, and this is the peak depth. Okay? Now I rotate the polarizations a little bit. What happens? Well, theta starts to get bigger than 0. The cosine goes down. The sine goes up. In fact, near the origin, this thing looks like a linear gradient in z. And a linear gradient magnetic field is familiar from the Stern-Gerlach effect. What you get is a splitting of the different magnetic sublevels in the presence of a max gradient magnetic field. And that shows up in these optical potentials in the following way. So here's the origin now. The modulation depth is now no longer perfect because of this fictitious magnetic field. And we get something that looks like this. Let me see if I can try my very best to do it. Oh God, terrible. It's just awful. Yeah. All right, I'll try it. This guy is too fat, it's the problem. So, here we are, and here's what we got. Well, I'm sorry, but this dot's supposed to be over there. That dot's supposed to be over there. The point is the following. What we get is a splitting of the spin up and spin down potentials, right? And they're split by an amount that has to do with this angle, theta. In fact, although it doesn't look like this, what you have here is a kind of double well potential. You have a set of what we called back in the day, this is something that I worked on, developed years ago, this is what we called an optical bipotential. In other words, there's a double well at each lattice site. So the lattice is still periodic with period lambda over 2. But each period has at each site, there is a deeper structure. That structure is associated with the spin and the internal state. In fact, what would happen if I took this lattice and now I embedded it in a true magnetic field in the x direction? Well, what would happen if I didn't have the optical lattice and I put the spin in a magnetic field along the x direction? It would precess, right? And it would go from spin up along z to spin down along z to spin up along z to spin down along z. What happens here? Any guesses? Well, it's going to try to do that, but what's going to happen is now in order to go from spin up to spin down, it has to tunnel. So we can think about a kind of gap forming in this lattice in which the atom, in order to go from spin up to spin down, it tunnels across this barrier. And it's one of the things we worked on. We saw an experiment where we monitored the tunneling of the atom in this bipotential by monitoring the spin of the atom, and therefore seeing mesoscopic tunneling of atoms in optical lattices by measuring their spin. In fact, the motion of this classically turns out to be chaotic. So there was an interesting connection between the spectrum of the system and quantum chaos. Okay, so optical lattices are rich, even in 1D. Even in 1D, you have more than just simple band structure. You have the spin dependence, which is arising from the non-scalar nature of the atomic polarizability. The final thing that I want to discuss today is higher dimensions, where things really get interesting. We won't say that much about it, we'll just give a little preview of that. So, let's see, my notes here. Right. So, what I mean by higher dimensions is the wave vectors have their axes along more than one direction, not just as the axis. So, for example, so higher dimensional optical lattices. Let's say I have a 2D lattice. So what I mean by that is I have wave vectors in a plane. Let's say I have 3 laser beams that are directed, for example, at 120 degrees, pi over 30. 60 degrees, excuse me. All right, so what is the optical potential associated with such a thing? It's going to be a higher dimensional variation. It's not just a standing wave along one direction, it's some variation in the intensity and polarization in 2 dimensions. In fact, this creates a 2D crystal for atoms. Generally, let's suppose that we have some laser field, which is some combination, linear combination or superposition of plane waves with some arbitrary polarization. And maybe some phase between them. Okay? So we have all these different wave vectors, different amplitudes, potentially different polarizations. Then my light shift potential of the general form that we wrote down before depends on all of these different terms in the superposition. So, what we have is all of these interference terms. If we just had the 2 beams, then we had that interference between the 2 beams. which gave us the standing wave. But now we have the differences between all of these different wave vectors, giving different modulations in space. In fact, this potential is of the form as a Fourier decompositions into components with different, what we call reciprocal lattice vectors. That is to say, if you remember, or if you've ever studied anything about a crystal lattice is such that if you take the potential and you displace it by some crystal lattice vector, R alpha, it goes back to itself. Just like in 1D, we moved it by lambda over 2, it came back to itself. Now I have, in three-dimensional space, different directions in space where I can move and get to the same lattice vector. If K alpha dot R beta is delta alpha beta, then this satisfies that relation. What we said, 2 pi in there? Yeah. So, what we see is that when we interfere a bunch of laser beams together, what we get is a crystal lattice with a set of lattice vectors that depends on the difference in the wave vectors. Let me just show you a couple of pictures, and we'll pick this up a little bit more maybe next time. But I wanted to show you just because I think instead of writing a ton of equations, it's easier to just look at a picture. And after we conclude, we do have the lovely idea forms for you guys, so I would really appreciate your feedback. And so don't run away. All right, let's see. All right, so what I'm drawing here, or what's being plotted here, is this configuration of laser beams where all of the polarizations are linear in the plane. And what that generates for us is a lattice which is triangular, but a bipotential, with sigma plus and sigma minus displaced relative to one another. If the polarizations were such that these polarizations were out of the plane, I would also have bipotentials, but in a more symmetric kind of lin-perp-lin configuration, with kind of this anti-paramagnetic order. So all I did, this is a little mathematical program, this just tells me the positive plus and minus potentials, P for spin up and N for, that's plus and minus spin up and spin down. That's what I did. And it looks at the intensity of plus and minus, sigma plus and minus electric fields, and then puts the Clebsch-Gordon coefficients in front. Okay? And so here's what you see. You see this is the contour plot. I should shut this slide as well. Of that. And perhaps this is a more descriptive picture. If this is the modulation of that potential in 2D as a function of x and y. And what you see is a kind of virtual egg crate for trapping these atoms. And this really has excited a lot of research because this is a kind of virtual crystal for the atoms, in the sense that what's binding the atoms is not their interparticle interaction, it is their binding to the light. And that is a dynamically controllable potential. In principle, one can change the polarization, one can move the atoms apart, or one can change the intensity, one can change the rate of tunneling of the atoms between those sites. And that gives a lot more flexibility in terms of studying and designing much of what is usually the domain of condensed matter physics, now in the domain of cold atom physics. All right, so on Monday what we'll do is just give a brief introduction and overview of one of the other most important developments of the last 15 years of cold atom physics, and that is the observation of boson-Einstein condensation and manipulation of quantum regenerative gases. So we'll give a little discussion of that on Monday. All right? Great. All right, so let's see. A couple of things. I have your last homework here for you on the last official day of class. If you can